Imagine a ticking clock, literally counting down to the exact moment our modern world goes dark. What actually happens when our fragile, highly interconnected technology collides with the absolutely chaotic, unpredictable wrath of the sun? Every 11 years or so, the sun just ramps up its magnetic fury. We're talking threatening to crash satellites, ground global aviation, and literally bring power grids to their knees. But what if we could actually predict its next strike? Welcome to this explainer. I'm incredibly thrilled to have you with us today because we're diving into an absolutely massive scientific breakthrough. We're going to decode the chaotic and seemingly totally unpredictable 11-year solar cycle. By digging into some cutting-edge mathematical analysis from recent astrophysical research, we're going to see exactly how scientists are building a solar clock to predict future space weather with frankly stunning accuracy. Okay, so let's dive right into our roadmap for today. First, we'll cover the very real threat of space weather, followed by the historical mystery of the solar cycle. Then we'll look at building a solar clock, uncover the switch-off predictor, and finally, we'll use all of that to predict cycle 26. Starting off with Section 1, the threat of space weather.
It's super vital to understand that sunspots and solar cycles, they aren't just academic curiosities for astronomers. They're the driving engines behind extreme space weather events that have a massive, profound impact right here on Earth. Just look at the vulnerable tech we're talking about here. We are looking at our entire modern infrastructure. A severe solar storm can induce currents that literally melt down transformers in our power grids. It disrupts the communication and navigation systems that our aviation industry relies on. It scrambles GPS globally. And recently, we've even seen unexpectedly high ionospheric drag, which basically acts like a thick atmospheric soup, literally pulling multi-million-dollar satellite constellations right out of low Earth orbit. So yeah, this is exactly why we desperately need advance warning.
That brings us to Section 2, the solar cycle mystery. To get that advance warning, we obviously need to predict the overall level of solar activity, and we measure that by counting sunspots, the sunspot number. But predicting this roughly 11-year cycle, which is known as the Schwab cycle, is just deeply, maddeningly chaotic. Looking at the historical data dating all the way back to 1749, you can really see the chaos. You can clearly see a cycle happening, sure, but notice the jagged, wildly varying peaks and valleys? Over the 25 recorded cycles spanning hundreds of years, literally no two cycles have ever shared the exact same amplitude or duration. Some peak high and fast, while others are low and slow. This crazy variability is exactly what has made predicting the next solar maximum a huge unsolved problem in physics. Moving on to Section 3, building a solar clock. Let's talk about wrangling that chaos.
So how in the world do scientists wrangle this? If the periods are irregular, you obviously can't just use a standard calendar. You need a totally new tool. Enter the scientific detective's secret weapon, the Hilbert transform. Now, without getting bogged down in all the complex equations, just think of it like this. Imagine a human heart suffering from a highly irregular, unpredictable arrhythmia. Sometimes it beats way too fast, sometimes slow. Well, the Hilbert transform is kind of like a mathematical magic trick. It takes that irregular heartbeat and forces it onto a perfectly steady, ticking metronome. It translates messy, unpredictable time into a beautifully uniform, predictable phase.
Here's the really elegant three-step method the researchers actually used. First, they take the incredibly noisy monthly sunspot numbers and they smooth them out over a 13-month rolling window. Second, they subtract the slow 40-year background trend, also known as the Gleisberg cycle, so they're left with just the pure, roughly 11-year oscillations. And finally, they apply that Hilbert transform to this cleaned-up data. They essentially stretch and squeeze those irregular cycles until every single one perfectly fits onto a uniform 360-degree or 2π analytic phase. Now let's see how this actually looks in practice. Up top, you're seeing the raw, jagged, wildly varying historical data. It's a complete mess, right? But watch what happens below that after applying the mathematical steps we just talked about. That chaotic signal is wrangled into a series of perfectly uniform diagonal blue lines. The absolute brilliance here is that we've taken a completely unpredictable timeline and mapped it onto a totally regular ticking solar clock. Every single cycle is now mathematically the exact same length. Which leads us perfectly into Section 4, the switch-off predictor. Because we now have this uniform phase for every single past cycle, we can finally identify critical moments in the sun's behavior that were completely hidden in the messy raw data. And the most important moment of all, it's something called the switch-off. Now, the switch off is precisely what it sounds like. It's the exact moment on our new solar clock when the sun transitions from its violently active phase into its declining, quiet phase. Physically, this happens when the bulk of active region sunspots migrate to within 15 degrees of the solar equator. Right at this moment, the whole nature of space weather shifts dramatically. The violent coronal mass ejections that cause the absolute worst geomagnetic storms here at Earth literally switch off, and they transition into much more moderate, high-speed solar wind streams.
And here is the magnificent aha moment of this entire research. Check this out. Scientists discovered that if you look at the specific sunspot number at the exact moment of the switch off in one cycle, it acts as a remarkably accurate early warning system for the absolute maximum peak of the next cycle. Because the switch off happens years before the next maximum, this discovery gives us a massive 7-year lead time to prepare for the next wave of intense space weather. 7 years.
And I really want to emphasize just how strong this predictive relationship is. The Pearson correlation coefficient for this predictor is a staggering 0.84, with an R-squared value of over 0.7. Now, if you know the messy world of astrophysics, you know that is incredibly high fidelity. What it means is that when scientists tested this method backward, basically hindcasting past cycles 1 through 25, the switch-off number successfully predicted both the massive peaks and the shallow peaks, with just incredible accuracy.
All right, let's move to section 5. Predicting cycle 26.
So, let's bring all this incredible math and data back to the present day. How do we actually use this 7-year lead time to predict our upcoming solar cycle 26? You know, the cycle that will dictate the safety of our technological infrastructure over the next decade. Well, there's one really vital caveat we have to keep in mind. As of the writing of this study in mid-2026, our current cycle, cycle 25, is still highly active. We haven't actually hit the switch-off moment on the solar clock yet. Based on the data, the cycle 25 switch-off is still about 2.5 to 3.5 years away. So to make a prediction for cycle 26 right now, researchers can't just simply read the clock. They have to use statistical models to project the current data forward to estimate exactly where that switch-off point will land. To figure this out, researchers used 3 major, completely independent forward projections, one from NOAA, one from the Macintosh model, and one from the NMSA. Because we're projecting into the future, the confidence bounds, which you can see represented by the shaded bands, they are quite wide. However, all 3 models point to the exact same conclusion. The projected sunspot number at the upcoming switch-off points towards a weak to moderate cycle 26. So we're looking at an upcoming cycle that is roughly equal to, or perhaps even a little bit weaker than, our current cycle 25. But there's a really exciting twist here that's going to help narrow this down very soon. Notice the concept of a duty cycle? That's basically the ratio of time the sun spends in its active phase versus its quiet phase. Well, the data reveals that weak and strong cycles group very differently based on their duty cycle. Because weak cycles behave way more predictably in this regard, once we actually cross the official switch-off point in a couple of years, all those wide, shaded uncertainty bands we saw in the previous projection, they're going to shrink dramatically. We will literally lock in a highly precise prediction.
Which leaves us with this final, crucial thought to ponder. We now have an incredible mathematical clock capable of untangling the chaotic nature of our sun. In just a few short years, the solar clock will strike the switch-off for our current cycle, permanently locking in the exact fate of cycle 26. Given our profound, ever-growing vulnerability to space weather in this hyper-connected age of ours, when that clock finally strikes, will we be ready for what comes next?